Stereo vision allows to retrieve 3D information of a scene by processing a pair of captured images. Usually, a stereo camera is employed to simulate the human binocular vision system. Given a pair of stereo images satisfying the epipolar geometry, it is necessary to find the correspondence of each pixel in one image and the other image by scanning epipolar lines. The location differences of all corresponding pixels in the stereo images form the disparity map of the scene. For each pixel in one stereo image, a small image fragment is constructed. Each resultant image fragment contains an implicit target with unknown shape centered at the origin. The target is embedded on a non-overlapping background with unknown statistics. The target in each image fragment is detected and located in the other stereo image, along the horizontal line by linear correlation. The depth distribution of the scene can be retrieved from the estimated disparity map, the lens focal length, and the camera's ocular distance. The disparity map can be estimated by performing the linear correlation and using an adaptive match filter. Usually, the matched filter is constructed from a reference image containing the target given explicitly. However, in stereo matching, the target is given implicitly in the reference image constructed for all pixels to be matched. The shape of the target in the reference image is estimated using a Bayesian classification rule. The input scene fragment is represented by a non-overlapping image model by assuming that the location of the target is unknown. The non-overlapping image model is also used to represent the reference image by assuming that the target is located at the origin. A matched filter optimized with respect to the mean squared error criterion is designed to detect and locate the implicit target in the input scene fragment. This filter is adapted dynamically to the implicit target in the reference image. To evaluate the performance of the proposed method for three-dimensional scene reconstruction, an experimental setup was performed for the capture of stereo images. Here you can see the operation of the proposed method. A small image fragment is created for each pixel in both stereo images. A fragment of the left stereo image are considered the reference. A fragment of the right image is considered the scene. It can be seen that the shape of the target given implicitly in the reference image is correctly estimated and adapted. It should be noted a sharp correlation peak in the correct location of the target in the scene fragment. The location of the correlation peak is a disparity estimate. An accurate disparity map is obtained. Here you can see the raw estimated disparity, a refined disparity map obtained by standard post-processing, and the estimated depth distribution of the scene showing the metric distances of the scene objects with respect to the camera. Several views of the three-dimensional scene reconstruction from different perspectives are shown. The proposed method was tested in different experimental scenes, obtaining accurate length measurements results. The effectiveness of the proposed method was verified in reconstruction of different experimental scenes.